All right, chemistry people, we are back. This one, again, should sound familiar. We're going to continue talking about making qualitative or quantitative prediction about galvanic cells based on half-cell reactions and potentials, and then analyze those cells to identify properties of the underlying redox reactions. Again, since that's like the third time that you've seen this content objective, we're going to talk briefly about some different aspects of this content objective in terms of what we're going to be doing to analyze those cells and identifying some of the properties of those underlying redox reactions. So if we break this one down for us a little bit, some of the underlying things that we're going to be talking about here to better understand those redox reactions are relating the equilibrium constant K, which we just began to understand and think about, to Gibbs free energy. So another big term there that we will just introduce in this unit and come back and hit later in another unit. We're going to be able to calculate Gibbs free energy, and then really all we're going to need to do is plug and chug into a formula and then think about how the value of your Gibbs free energy change relates to the spontaneity or thermodynamic favorability of the reaction. And then lastly, you're going to calculate cell potential under non-standard conditions, which is a little trickier than under standard conditions, but doable. All right, to start, standard Gibbs free energy change and K, the equilibrium constant, are related by the equation that's expressed here, and is the change in free energy when all substances in the reaction are in their standard states under standard conditions of 1 molar solutions and 1 atmosphere pressure. As you take a look at your equation that relates Gibbs free energy change and your equilibrium constant, it looks really complex. At this point, we're just going to plug numbers in and chug and sort of see what the sign is for your Gibbs free energy to help us understand what's going on with that redox reaction in this electrochemistry unit. All right, so if we break down your equation that relates the Gibbs free energy change to your equilibrium constant, you get this on a formula chart, so it's not something you have to remember. Just keep in mind that your equation breaks down to the negative of the gas constant R. Be careful here, you've got several gas constants R on your formula chart to reference. You want to make sure that you use the energy one in this example because we are talking about Gibbs free energy. So here we will use the 8.314. Your temperature again has to be in Kelvin, and then K is your equilibrium constant. And then we'll talk about mathematically how you can rearrange the equation to solve for the equilibrium constant. If you're a math genius, you may already know how to do this. Just using some awesome algebra skills to solve for something else in the equation. All right, so some quick things here to take away from the Gibbs free energy formula that relates the equilibrium constant. 1, if your equilibrium constant is equal to 1, that means, of course, you got significant amounts of both reactants and products at equilibrium, and therefore, when your equilibrium constant is equal to 1, then your change in Gibbs free energy is equal to 0. Okay, and if we think mathematically sort of what this means, if you take the natural log of 1, you get 0. And so if you plug 0 back into this formula, 0 times whatever Kelvin temperature times whatever gas constant you decide to use, although it should be the one for energy, you're going to get a value of 0. So when your equilibrium constant is 1, the change in Gibbs free energy is equal to 0. So if your K value is less than 1, there's a larger concentration of reactants at equilibrium. And therefore, your Gibbs free energy change is going to be greater than 0. What this implies is that your reaction, as you have it written, is endergonic. That's a key word there, endergonic. It requires energy to occur. This is also described as a not thermodynamically favorable reaction. It's a key word you want to use there, not thermodynamically favorable, old school, non-spontaneous reaction. It's not going to happen as written. Now let's think about this. Let's go back to what our equilibrium constant expression looks like. If we have a K value that is less than 1, essentially keep in mind that means that we've got a lot of reactants at equilibrium. And so when you take a natural log of a number that is less than 1, you're going to get a negative value. And so a negative times a negative here is going to give you a positive delta G value. And again, this is not thermodynamically favored when you've got those positive delta G values. Again, it implies that our reactants are favored. And so as written, we're not going to form those products. And that's all this positive sign is telling me, that it's not going to happen as we have it written. Okay, on the other hand, if K is greater than 1, again, what that means is that there's a larger concentration of products at equilibrium, and then delta G, or your Gibbs free energy change, is going to be less than 0. This indicates the reaction, as it is written, is exergonic. Exergonic releases energy. This is also described as a thermodynamically favorable or spontaneous reaction. And so again, sort of tie this back to our equilibrium constant expression. If you have a K value that is larger than 1, it implies that you've got a larger concentration of products at equilibrium. And if you take the natural log of a number larger than 1, you're going to get a positive value here. And then a positive times negative is going to give you a negative value overall. Okay, and then sort of the last thing we need to talk about here for today is how can we calculate the cell voltage under non-standard conditions. So when we don't have those nice 1 molar concentrations, what is the voltage going to be? And so keep in mind that all voltages that are calculated using the standard electrode reduction potentials assume standard conditions. But sometimes, like in the lab we're going to do, those conditions are not in effect. It's important to note that as a voltaic cell discharges, so think of like a battery, your reactants are consumed and your products are generated. And so the concentrations of your reactants and products are going to change. As the cell operates, then the conditions become non-standard, and the voltage is going to drop. So again, as we go back to our equilibrium constant expression, initially you may have a lot of reactants typically when you're starting your reaction, but as that reaction proceeds, the concentrations of your reactants are going to change, and therefore you're not going to be at standard conditions. Lucky for us, there's a really amazing formula that will help us determine what the cell voltage is when we're on non-standard conditions, or we're under non-standard conditions. And that equation is known as the Nernst Equation and is expressed to you here. This equation is no longer on your AP chemistry formula chart, and according to College Board, you do not need to use this formula. However, I find it helps me to better understand what's going on when we're at non-standard conditions. And so I would encourage you to commit this equation to memory because you can still use this on, say, a free response when you're trying to explain what's happening under non-standard conditions. So sort of as we break this down, note here just the difference between these two. The little naught symbol there is going to indicate the standard cell voltage under standard conditions. And so whenever you're trying to do it for non-standard conditions, we're not going to see that little naught symbol there. So when we're solving for non-standard conditions, we need to take whatever the cell voltage is under standard conditions and subtract from it RT over NF ln Q. Which means the product of the gas constant, again, you want that energy constant there, the 8.31, times the absolute temperature in Kelvin over the number of moles of electrons exchanged in the reaction. This is why it's so important to balance those redox reactions, those half reactions, before you add them together, times what's called Faraday's constant, which is 96,500 coulombs per mole, and multiply that by the natural log of the reaction quotient, Q. Many times, and this is probably the one that I would memorize if I were you, the Nernst equation is used when we're talking about room temperature. So even though our concentrations will change from standard, 25 degrees Celsius is a pretty reasonable temperature Okay, so this is the equation that I would actually memorize. It's sort of rewritten and simplified for when we're working at room temperature. So just they've combined that constant, that gas constant, the temperature at 298 K, and Faraday's constant to give you 0.0592 over just number of moles times the log of Q, which I think is a little easier and definitely something worthwhile to commit to your memory. However, if you do not want to use that mathematical expression, the big thing to take away is just this. As the concentration of the products of a redox reaction increases, so as you make more product, the voltage is going to decrease. And then as the concentration of the reactants in a redox reaction increase, so if you're forming more reactants, your voltage is going to increase. Okay, so again, as you're trying to make sense of this equation, I've just replaced the reaction quotient Q with what its expression is, your product concentrations over your reactant concentrations. And so as you think about a reaction proceeding and forming more product, so your concentration of products is going to increase. What that means is when you take the natural log of a number that's larger than 1, and it maybe can progressively gets larger and larger than 1, what that means is you're going to get when you take the natural log of that number, you're going to get a number that's progressively more and more, well, a bigger positive and positive number. And so when you are then subtracting a bigger positive and positive number from your standard cell conditions, you're going to end up with a cell potential that is less than the cell potential under standard conditions. However, on the other hand, if you are forming more reactants, your reaction quotient Q, when you solve it, is going to be a number that is less than 1. And when you take the natural log of a number that's less than 1, you are going to get progressively more negative numbers. And when you ultimately end up subtracting more negative numbers from your original standard cell value, your cell potential under those non-standard conditions is going to continue to get bigger and bigger and bigger. So this is just some math that you have to wrap your mind around. But again, the big takeaway here from the Nernst equation is that as you use up your reactants and form your products, the cell voltage is going to decrease. And then if you are forming your reactants, as shown here, as you're forming your reactants, your cell voltage is going to increase. Just keep in mind again that the only difference between standard cell voltage and cell voltage under non-standard conditions is just that little naught symbol. And then lastly here, just keep in mind that you can also create what are called concentration cells, which are made from two half cells of the same metal ion combinations, but with differing ion concentrations. And when you do have a concentration cell, the electrons will flow from the lower concentration half cell to the higher concentration half cell in order to achieve equilibrium. And we'll look at a quick example to help you better understand that. Ultimately, though, here is the big takeaway. All of these notes and all of me talking at you can be summed up in this one data table. So as you are reviewing and practicing for the test, you want to be very familiar with the relationships that exist between the standard cell potential, Gibbs free energy change, and the equilibrium constant, and sort of what that means when you have those different values. Again, use those formulas that are provided to you on the formula chart to sort of help you make sense of these different relationships. Done.